Thank you so much for that thorough introduction, and thank you also for the invitation. It's really a pleasure to show our work, my work at ICD, and the work that my colleagues also conducted at the same institute. And it's true, I'll probably say would a lot of times, but what I will try to do in this lecture actually, I want to contextualize not necessarily the material that I'm working with mostly, but also mostly the technology that I'm working with, and how computational design and digital construction enables us to rethink how architecture is made, how it is produced, how it is designed, and how basically technology becomes an enabler of a new kind of architecture. And that definitely applies to both wood and masonry, and I think as basically those two are the most, the oldest and the most common building materials, you can definitely see that they have something in common, even though the material itself is obviously very different. But let me start actually in a more general way by introducing how we work at the ICD, how we conduct research, how we transfer really basic research that we do into architecture, and how we try to showcase it, to evaluate it by making demonstrators, prototypes, buildings, and kind of going through the whole endeavor of what you would normally have in classic traditional architecture, where you would have a lot of contractors, a lot of hierarchies involved, and how we try basically to allow our research to also restructure how architecture is being made nowadays. You can really divide it into three absolutely basic research interests, and that is computational design, which basically means everything that is done on the computer in algorithmic form. Algorithms that model, that simulate, that form-find shapes, that can lend ideas from evolutionary design, biological role models, and so on. The second one being robotic or digital fabrication in general. And that's not only because those robots that you might have seen already many times on Facebook in the last few years, it's not only because they are orange and fancy looking, but because robots are basically a little bit like iPhones or smartphones in general. They are a platform. Robots, compared to many process-specific machines, are basically only a very simple but enabling tool that we can use, and we can program our own applications onto them. And so we can basically strap a spindle, a 3D printer, or any kind of effector onto the robots, and then use them for a specific task. And so we use a very common tool, a very actually mass-produced, high-quality, high-accuracy tool, and give it many different purposes. That's why you will see lots of orange robots in this lecture. And the third is more or less a filter in our research, in basically the starting with basic principles of fabrication or basic material principles, and then translating them into different construction systems or different design tools. And by doing that, we usually like to look into biology, and we try to find role models, basically, that allow us to kind of focus on what makes the most sense. I'll go through a few examples that kind of showcase how we're not trying to copy biological shapes. This is not any kind of classical Renaissance idea, but it's more like a functional biological research that we are doing. Also, to clarify, in case this is something that many people confuse sometimes, there's a really big difference between computerization and computation. Computerization is basically everything that has become digital, that was digitalized in the past, and it's of course very important to digitalize processes so that they become more efficient and faster, and we can kind of focus on what's actually important. But if you only digitalize the classical architectural design process, you are still manually producing this result that you can see here. And So basically, you are the author. You own, as an author, you own the outcome, the final design of the product, and computation does something else. In computation, you are the author of the algorithm, basically, of the process or even of the principle that generates the outcome. And of course, that would allow you to basically produce many, many outcomes, hundreds and thousands of iterations of outcomes that would then allow you to evaluate them and to kind of choose the best one that basically it has the most advantages in terms of whatever parameter, whatever evaluation criteria you want to apply to it. So that's a big difference. And obviously this is happening nowadays in many different sectors of architecture, but allowing this general idea of computation to go through all of architecture is what we really need in our research and what we hope will transfer ultimately into architectural design processes. So compared to industrialized construction, basically what we see what happened in industrialization is that through the restructuring of architecture, because industrialization allowed to introduce a lot of different hierarchies, a lot of different contractors basically only fulfilling a specific task. Also in the construction itself, in the structure itself, you see that most building elements are basically divided. You have a division of functionality and you have a repetition of elements. Since that basically is what happened during the industrialization, efficient machines that were powered by electricity allowed us to make a lot of the same components, and so it became very common to basically just try to do that. And compare that to Frei Otto's work, who's basically the founding father of computation. If you look at his work, you can see basically what he did is computation, not on the computer obviously, but in the physical world. He allowed the material with his tensile structures and his bending timber grid shells and all the research that he did on form finding, he allowed the material in its actual physical context to compute the shape that it can basically best serve, where it has the most efficiency from a structural point of view. So basically there's only a few parameters here, but these few parameters that you basically had in the physical world are the ones that he applied to his form finding research. And he did this on an immense scale, something that you wouldn't be able to do nowadays, or something that you can simulate nowadays in the computer. So it's really interesting that he built many of these structures in the 60s and 70s, and he couldn't use a computer, he didn't use a computer, he did model making, everything was manual and basically handwritten calculations, whereas if you look in the history of CNC machining and robotics, even 10 years before Frei Otto's most accomplished works, CNC machines were already developed, mainly at the MIT. In this, what's called the Milwaukee Matic 2 first tool changer, which actually a CNC machine that had already a tool changer, so it could mill with different tools at the same time. It is basically the same thing that we have nowadays in common CNC machines. You still have a very abstracted series of steps, of programmed steps that are produced, that are kind of made to make the machine produce certain movements that would then create a certain material, right? So it's basically very detached from the actual material and design process itself. And also at around the same time, these, what basically they are called anthropomorphic mechanical arms, were also kind of developed at the same time because they had, compared to the CNC machines, very specific advantages. Whereas in architecture, if you look back at the history of construction robotics, you will basically end up in the 80s and 90s, where in Japan, huge construction robots, so basically this whole thing is considered one robot, were designed and built to build buildings more efficient and faster. However, this actually didn't go so well, otherwise you would see them nowadays a lot more. And so due to many different reasons, way too complicated machines, but if you look at the grand picture of what are now called 4 industrial revolutions, you can see maybe they were a little bit too early in their development, and maybe nowadays we will have a bigger chance of automating and also, of course, individualizing architectural production. If you go through the history, you can see in the first industrial revolution, basically, that's what is generally be considered when first mechanical production facilities with water and steam power were used. In the second one, basically the division of labor and mass production with electrical power was what really drove the Industrial Revolution, what is actually considered an Industrial Revolution. And then in the third one, using basically when these machines like the industrial robot and the CNC machine were developed, basically what came in addition was using IT systems and computers to program the machines. And so what's happening nowadays is not so much what robots can do, but basically everything that's around those robots, everything that allows the robots to recognize parts, to sense their environment, to have every basically building element speak to each other. And so you have a much smarter production process. This is happening for many years in, for example, the car industry. And it has also, in a way, happened in architectural building construction research. You don't see that much nowadays on site, but what is happening compared, basically, if you look at the research facilities throughout North America and Europe and Asia, you can see a similar development. You can see the kind of offline programmed, very simple steps that are programmed to make something, something more adaptive, some structures that are very well adapted to a specific use, to a specific environment. But everything, in this case, in a lab condition, is very, it's very well. You basically have a very safe environment. You don't have any kind of inconsistencies in the structure and so on. Whereas if you look at construction robots that are actually on site, they have to be so much smarter. They have to have so many more sensors. You can see how the scaffolding is moving here, how everything is kind of shaking, and the robot is still adapting to that life, basically. And this is what they call online controlled robotics. And what we are trying to do is bringing these ideas of Industry 4.0 of having much more advanced fabrication or production chains, basically, into architecture, and by that allowing a much more adaptive, a much more performative kind of architecture to be built. It's not necessarily an argument to say something is too complicated or it has too many elements to make if it is automated. It doesn't really matter how many elements a building component has if you can just make the production process of it fast enough. And looking to the future, what we're also doing, a colleague of mine, Maria Jablonina, has done, allowing robots actually to take basically most of the decision making on themselves, and basically allowing the robots to be very intelligent building machines. What she has done is basically develop this automated robotic production where the robot is weaving fibers around these hooking points. And speaking about fibers, this is something that we're doing at the ICD as well. We're not looking into only one material. We are open for many, let's say, promising materials, and not only the classic ones, but also the ones that are used in the car industry and the aerospace industry. And one of them is carbon fiber. That's what's being used here as well. Why? I don't want to go too much into detail, but if you look in basically any biological building material, you will realize that all of them are basically fiber composite materials. Wood is considered a natural fiber composite, and for example, our bones and kind of the biological structures in animals are all made out of collagen fibers. And if you go down into that scale, basically, even in architecture, what it allows you to do is to not only think about how a material is being processed and assembled, but also how you can make the material to behave in exactly that way that you want it to behave. You can basically program and make up the material structure itself. And that is not something that's entirely new for architecture. Again, it has been done in the aerospace and car industry for a very long time. This is, for example, a mold for, I think, the new A380 wing that is made out of carbon fiber. So programming how the fibers are being laid onto this mold is something that comes very natural if you work with carbon fibers. Doing that on an architectural scale, however, if you want to build architecture, you have the problem, of course, in this kind of technique that you would have to make a mold for the building itself. And that's something that doesn't make much sense, although using a material like carbon and glass fiber makes a lot of sense because of its performative capacity, because of its structural performance. So my colleagues at the ICD have done an incredible, or completed an incredible body of work already by looking into how we can apply this material on a larger scale without making too much formwork, basically, having either very little formwork or some kind of adaptive formwork that you can use. This has been done on many different projects, always looking into some biological role model. For example, like here, looking into detail into the material organization of how crustaceans actually have very soft and very hard parts that are all made of the same material, and how that basically is only due to how their collagen fibers are aligned. This was in 2012, and this project applied on a very large scale on basically one single frame, producing very interesting fiber patterns that would basically overlay and form very rigid and also very translucent shapes. It was then in later projects basically made into components and modules that you could basically prefabricate and then put on site. So in a later project, again, there was a role model basically looking into how these fibers are arranged. In this case, it's the elytra of the flying beetle on the bottom left. You can see that this protective shell is actually, oh, that video isn't working. The protective shell of the flying beetle is actually super lightweight, but still very, very strong. This principle was transferred into some novel production process that was, in this case, produced by two robots working in parallel to weave these components, these cellular components that would then be joined and assembled on site. This has recently been evolved into a larger, wide-spanning roof system that was then made in a different way. So here, basically, my colleagues have always been combining a certain fabrication setup, a certain production logic, and what it allows you to do on an architectural scale. This has been exhibited, it's actually called the Elytra Pavilion, at the V&A in London and at the Ritra Design Campus afterwards. And you can see how these components they were made on site also, and then assembled kind of as the structure was growing in the museum. There was still a more or less kind of pre-programmed fabrication process, and what we have been trying to kind of engage into is much more adaptive fabrication processes to kind of see if we allow the machine to be more intelligent and to make more decisions by themselves, that we can take basically structural ideas much further, allowing certain fabrication processes to make ultra lightweight construction that is so lightweight that you kind of need to have certain adaptive fabrication processes where the robot or the machine is making decisions. In this case, it was based on a water spider, which is weaving or reinforcing an air bubble underwater, and by that kind of building its own home. And this was kind of inverted and making a pressurized bubble above water, obviously, and putting a robot inside and then reinforcing that inflated bubble by laying carbon fibers onto it, and then later kind of deflating the bubble and cutting in the openings, and the hardened carbon fiber would then carry the whole structure. And the last fiber pavilion that was built just last year followed a similar logic by lending some ideas from the leaf miner moth, whose larvae are actually spinning these kind of silk hammocks, kind of bending the leaf into a certain shape while it's spinning its cocoon. This idea of kind of this elastic bending that's also happening on the left robot, together with very like much larger structures that are large enough, like too large basically for one robot, so that then the fiber has to be transferred from one robot to the other, was kind of developed into a construction system with, you could say, multiple robots collaborating to build this 10 meters, 8 meters cantilevering pavilion. And in this case, unfortunately I don't have a video, but you can look it up online, I think. You can see that basically the drone has to carry the fiber from one robot to the other. So there is some interaction happening where the fiber is being transferred to the other robot. And so lots of sensors, lots of decision making that's happening live, that is not being pre-programmed basically. And so this is kind of the research that we're trying to engage in, that allows us to kind of make these really intelligent fabrication processes. And again, as all the other structures, we're talking about ultra lightweight construction here, just a few hundred kilograms to allow for this cantilever to work. What's especially interesting to our research in the computational wood architecture group is this idea that you have this very natural growing material that has very specific characteristics on a very small scale. So you in this case, you can't make wood yourself. You can't grow it in a specific direction, not quite at least, not on a cellular level, but you can really decide what you do with the material. You have really a lot of control on the structure of the material, and making it into plywood and any other really modern products also. A lot of question about how you combine basically the substructure of the material, which I think is also happening in masonry and in clay 3D printing. So you have a lot of decision making already in that process on the left basically, and then combining that with modern fabrication technology is basically what allowed us to look into very different ways of how to work with the material. And I want to focus in the lecture here a little bit onto the basically how we use the technology in this process and how it allowed us to develop a certain construction system, building system, and then how we actually build it also on site, ending up basically with a lot of also manual labor on the construction site. One of the bigger trajectories that we have at our institute is the research into segmented timber shells, basically looking into how we can produce panels of flat timber segments that are joined together to form a continuous shell structure. That was initially kind of enabled by a research into very classic timber joints, very classic timber construction, and looking basically into how, for example, this finger joint that you all probably know from IKEA furniture in the drawers, in the corners, or from basically very simple joinery, how we can transfer that very classic and also, by the way, very effective joint into architectural construction. It is a joint that was developed thousands of years ago. Because it is very effective, it was also used a lot. But basically through industrialization, since it is very complicated in a way, complicated to make with standard machines, it was kind of lost. And now that we have these machines again, it basically allowed us to rethink or to re-innovate this kind of joinery technique. In this case, all you need is a 7-axis robotic setup and a spindle, and that will allow you basically to mill any kind of finger joint in any kind of thickness, in any kind of angle. So we developed, compared to the standard CAM, computer-aided manufacturing software, we developed our own little manufacturing process, basically telling the robot to mill the boundary of this plate, and then the miter connection, and then the finger joint. So it's like 3 different jobs that it's doing on each edge. combined with this turntable that is actually just another axis of the whole robot system, so that's why they're moving so synchronous, which of course looks really cool too. But it really allows you to process a plate, in this case, from any direction. That's really important to basically, you're also designing in a way the fabrication system, and that's really essential in this case. That resulted in the first of many timber pavilions made out of a continuous plate structure. In this case, it was even double layered. Also, since this was a student project that we developed, there was no question about labor, time, and assembly time. So this 10-meter pavilion was actually made out of 750 individual plates. So it took a long time to actually assemble it. Well, longer at least than we thought, but it still, was done in like 8 weeks approximately. But building such a building on as a proper building on site with contractors, of course, it is essential to really have, let's say, an efficient surface division, to have not too many elements and to assemble them in a really quick way. So in a continuing project that was given to us and also extended by additional funding through the government, we started to actually transfer this general idea of having plates, planar plates, basically segmenting complex surfaces. We took this idea onto developing a real building system, basically, that could actually be used by a timber construction company. So this transfer from pure research and throwing 20 students at it to be built, and then not really thinking about labor time and so on, getting that into actual building construction with the usual constraints that you have, getting the permits, calculating all the connections and the actual structural behavior was a really important step. So in this case, there's also a lot of research going into the geometry, and I think that applies for all these kind of construction and structures. Having, by the way, a double curved surface just in general, of course, gives the whole building a lot more stiffness, structural stiffness. So we're not building these weirdly shaped buildings just because they look cool, but because they actually have some structural performance, because they, to some degree at least, follow the main load-bearing direction. They kind of are structurally optimized, but at the same time, of course, there's a design intent, so they kind of negotiate between the two. So that's why you will see that they sometimes exhibit some form that kind of relates to a hanging chain model, for example, like Frei Otto's designs, but then not entirely, because of course we also want to have some design input from the architect. But in general, having these doubly curved surfaces, especially the ones that you can see here, make a lot of sense from a structural point of view, but they are very difficult to segment, especially if you talk about timber construction or anything where you work with material that is still in a way standardized. So dividing them into a certain way is basically a design or geometry task or a challenge that we tackled with certain computational design tools that are basically simulating these plates, form finding the individual plates, and then basically leading to a certain layout of this kind of plate structure. And that ties into a lot of things. It's not only about making this structurally efficient and maybe even good looking, like finding a certain smoothness in the surface division, but all of what's happening here is actually based on a lot of external parameters. For example, the plate shouldn't be too big, it shouldn't be too small, it should be fabricable. So there is information about what's the maximum minimum size of the plate. There's information about what the stock material is that we're working with. So how can we later nest them, and that's what you see here, how we can later nest them into the stock material to be also material efficient in this case. And I mentioned fabrication constraints, so basically while we were developing this design tool, we were basically working with a robot manufacturer to look into what kind of robotic setup we could use to make these plates. And in this case, since this was still a research project, we actually borrowed a kind of pre-made milling cell, and that gave us a certain range of sizes of panels that we could produce. So this was really important to look into from the beginning. So basically, the design process and this development process here was looking into fabrication possibilities, into the stock material that we work with, and into the design at the same time. And not only that, of course, at the same time we were also developing with our structural engineers what kind of connection we could actually have in a real building that really needs to hold up for a longer period of time. So we didn't only have finger joints that would connect these plates, you would also have, in this case, a crossing screw connection, for example, that allowed more forces to be transferred. Interestingly, though, that in these kind of structures, a lot of in-plane shear forces basically are transferred over these finger joints, while you also have a few tension forces where the screws are really important. But so this moving model that you saw earlier is basically everything that we needed to then fabricate it. So what was happening in this development was that we also developed an algorithm that would basically read out the geometry that our design tool generated. That's on the left. It basically is just a few surfaces. And then it would automatically generate the tool path for milling the plate. So we didn't actually have the final geometry in our 3D model. We only had the surface on the left and then the tool path on the right. So basically our BIM model, if you want, is only comprised of a little bit of geometry data, but mostly fabrication data. This was then in collaboration with the timber manufacturer that we worked with. First of all, they were prefabricated, so they use standard machines in this case. So we looked into what machines do they have, what can be used, and basically how can we enhance it with the robotic setup. So they were pre-cut into stock plates, basically, and then mounted onto the robot, also the turntable again, and then milled into basically super high precision in this case to make these finger joints really have material contact later on site. Of course, that's not how it looks like. This is more how it looks like. It's really also a messy kind of work that you have to engage with. But you have to, as an architect, and we are architects, you have to engage with the machine. You have to understand how milling works, for example. You have to understand what kind of milling tool you need, what diameter it has, what is the speed of the spindle, and so on, and what's the outcome later once you mill it, what's the surface quality, what's the tolerances that you have. Especially with this kind of construction, you really need the material, the finger joints to touch so that they can transfer the forces later. So we were basically on site with the timber manufacturer making these components. We also tried to pre-mill these crossing connections to really ensure that these angles of the screws were correct, so that we had basically that stiffness, that structural performance that was calculated before. But not only the structure, I mean, this is of course about a few more construction layers that you have usually. It was not really a completely insulated building. It was actually considered a kind of a cold building that would only be used in summer. So we only had a little bit of insulation, but we had the insulation layer, we had the waterproofing layer, we had the cladding, and all of that, of course, has a complex geometry. So we had no choice but to prefabricate everything digitally. So the insulation was wood fiber plates that were also 5-axis cut. We basically automatically produced the machine code for that as well. The waterproofing layer was EPDM, and there was a water jet cut, so we also produced the code for that. And then the timber manufacturer put that together into sandwich panels and then put it on site. So basically you end up with this kind of huge puzzle that was put together surprisingly quickly. This was an experiment, of course. The timber manufacturer knew that if something doesn't fit, you can't assemble the building. You can't have your usual timber tools like a chainsaw and cut off a little bit of a finger and then it would fit. This wouldn't work in this case. The building only fits together in exactly that shape. So having the tolerances under control and having also under control that you assemble it in the right, in the right position in space was really essential here. But it's a very redundant system. It kind of shows you when you go the wrong direction. It shows you how it wants to fit together. And so it was a really quick process. It was actually assembled in 3 weeks with 4 people. And the good thing is, of course, that having such an integrative development process, that you also think about how the interior space will actually look like. And it turns out that having these segmented shells as not only the structure, but also the kind of the space-defining boundary makes for very interesting aesthetical and spatial impressions. Working with that material, and I think with every material that is segmented and where every building part has a slightly different texture, slightly different color, makes for very interesting impressions. Oops, I'm sorry. So I want to show you this video because I want you to see this whole development process basically in 2 minutes. Obviously, there's a lot of emphasis on the material because, as you can imagine, the industry is also funding us in certain ways. So they wanted to show also how the material is made. In this case, by the way, this is beech plywood. Beech, using hardwoods like beech as building materials is something that's also kind of new. And it was actually the first building, to our knowledge, to be made entirely out of a hardwood construction material. I haven't mentioned the parallels to the biological role model in this case, but there are biological systems that are made out of individual plates. And so it's very interesting to see how they are constructed, and we transferred a lot of logic in kind of the geometrical arrangement of these plates into our design tools. So you have this as the basis of your fabrication process, and basically this is everything you need to engage with the machines. But if you look at it from another point of view, what has changed in the timber industry for this timber manufacturer? The only thing that changed is that we borrowed a robot for a few weeks to have a slightly more complicated milling process, something that you could probably do with a 5-axis milling machine in any case. They had all the other machines. So all we did was, if you want to kind of exaggerate, all we did was we changed the way we look at how we can use the machines and how we can access the machines. There's a lot of digital design behind it, of course, but basically by thinking about what kind of machines are available and how we can employ them, we also changed the way how we develop these construction systems and how we design with them. So in this case, the robot was really just used as a pre-programmed milling machine, and basically from there on, we have been trying to look into the next level in a way, to not only have the robot as one particular tool, but to have an entire production process that is automated. So in our current research, we are taking this a little bit further. We are taking, for example, into account the structural capacity, having optimizing algorithms that happen in the background, having ever more intricate, more complicated construction systems that need a lot more prefabrication, that need more complicated tools, but that can basically fulfill this necessity to have more material saving, more material efficient, energy efficient structures. We're currently trying, we've made some studies, and we're currently trying to build much larger shells. In this case, this might happen next year, which would be a 13-meter spanning timber shell made out of these modules. A slightly different approach is in a project that I did actually with David at ISTD and before already. And it's integrating a few different material aspects. It's integrating on the one hand something that is where David is working on now as well, which is the hygroscopic, the humidity reacting capacity of the material. But on the other hand, it's also using the elasticity of the material. And you can see these components are actually curved, they're bent. So it's a very different approach to like standard timber construction, where you basically use the material as a solid, very rigid material. But if it's very thin, wood exhibits a lot of elastic capacity that you can really use to make much more complicated structures without, forcing it into shape, without milling it into shape, for example. We've tried this on previous projects on a kind of global scale, and in this project we did this on a modular scale. So this, what we call the hygroskin pavilion, is actually comprised of modules that all have the same cone shape as a basis. So all of these modules are actually just intersections of the same cone shape and are made from flat material. So they're basically prefabricated panels that are, by connecting them, kind of pushed into their elastically bent cone shape, and then two of these layers are combined with insulating foam on the interior to make them into a solid kind of structural segment that is also, again, super lightweight. So here, since all these components are made from the same cone, we used a very standard manual fabrication process in the beginning to kind of prefabricate those kind of stock cone modules. And so we made a very precise vacuum molding setup. Again, we used the robot basically as a CNC machine here to kind of ensure that this would be a very precise shape. We scanned it to make sure we assembled it in the correct way. And then having this module prefabricated manually, we would then afterwards, in this case, so we wouldn't use the robot in the beginning, but we used the robot in the end. We would mount it on the robot setup, and we would then measure where in space the component is, and then kind of rearrange the fabrication file to then precisely cut out the edges of the component. In this case, we actually used a saw blade on the robot that would cut along these curved edges, and a foam cutting tool on the interior. So because all these components were curved, it was really crucial to have this additional feedback to kind of use the robot to measure the component and then update the fabrication files to ensure that we would be able to cut them in the exact geometry. Otherwise, you would have steps between those components. The gaps wouldn't look, or the gaps wouldn't be parallel. And this was a project we did for the Frac Centre in Orléans in France. So it was basically a museum piece, and we wanted to basically assure very high quality in this case. I'm pretty sure in some other lecture, David will tell you much more about these hygroscopic components that actually open and close in reaction to humidity changes. The biological principle here is a pine cone that also opens basically when the humidity drops because of its individual fiber arrangement within each of these scales. And so this was transferred by our colleague Steffen Reichert many years ago already, in kind of a bi-layer component. And that was then further developed by David, even down into 3D printing. In this case, they open and close on a daily basis. Basically, in the morning it's very humid and they are closed, and when the sun comes out, the humidity drops and they open up. So again, this is a very different way in integrating the technology part of fabrication into the overall development and when you want to actually apply it, compared to a simple milling process where you still have to afterwards, work on the building element, kind of, you have to sand it, you have to make sure the surfaces are correct, and in that case we use the robotic process in the end to kind of ensure the precision after all the manual process. But a lot of this research, also to wrap it up, is not only about the use of the fabrication technology, but also about how and when you want to use what kind of material or what kind of products that are available. And I think there are also a lot of similarities to other materials here, because timber comes in many different shapes and in many different products. And so the question is always, are you going to use what's available in the most efficient way, or are you going to kind of cut it down into the pieces and the geometry that are most suitable for your kind of construction system? So in many projects you also think about, can we use stock material basically to be assembled into more complex shapes than just rectangular buildings? Can we use standardized material on complex surfaces without having to prefabricate and process every single element all the time? And I think this is a very important question not only for wood, because processing every single element and then assembling it again into a more complex structure also means that you have to give every single element a certain ID, you have to have a certain plan, a certain process that allows you to also know which element goes where all the time. So we think about ideas how to use stock material. It doesn't necessarily have to have an ID, a tag, but that basically frees you in a way so that you have a certain structure that kind of indicates where you put the stock material, and by that you have a much more efficient building process. And this is the workshop that we just did in September. David and I went to UBC Vancouver and had a little workshop there. And it's basically this idea brought into a certain facade system, a certain facade structure, and where you have a prefabricated substructure, but then you put cladding on it that is actually just stock material. So the idea is that the substructure is highly individualized, CNC cut, a diagrid basically, but it is kind of, the instructions on how to assemble it are already in a way engraved into these individual strips, and so the assembly of these strips is possible without having any plan drawings, without having any instructions. And then once that is assembled, by having some indication points on this substructure, you know exactly where to put the planks. And these facade planks are completely straight. They are standard cedar cladding planks, and you simply put them on point by point, and by that you also make this whole structure very rigid. So both the planks and the diagrid substructure have structural purposes, and together they kind of form this very rigid system. So we had in this case also some kind of automated design fabrication process that would basically export the fabrication data directly, and we use the robot here simply because of the large workspace. Again, it's a more or less normal milling process, of course very individualized, very automated in this case. All these elements have a different shape, but the fabrication code is automatically generated. And we simply use this large, in this case 6 meter long linear axis. It just makes the robot to have such a large workspace compared to normal CNC machines. So that allowed us to very quickly produce this diagrid, to assemble it, and then basically put on these planks by simply following the intersection points of the diagrid. And so you kind of have this very individualized complex surface where the planks are actually overlapping in the middle. You can see they're actually forming a completely closed facade. But then depending on this curvature of the whole system, they open up on the left and on the right and kind of make it a bit more transparent. And you have this very smooth surface on the one side and a very detailed diagrid on the other side. So these are basically the questions that we try to look into. We are very lucky that we have a lot of partners from industry, from other research institutions. As was said before, we work with engineers and biologists together to kind of have this integrative design or development process. It's very important that you look at everything that's involved in architecture basically at the same time, which makes it very complicated, of course, to also explain these projects because everything is happening at the same time. And we're not looking only into the material, we're looking at how the material is processed at the same time while we're developing this kind of construction system. We develop the fabrication process and then also the design, of course. And we want to showcase, and that's really important in architecture, you have to showcase what is possible by making these prototypes and making architecture-sized demonstrators so that it is also becoming visible of what's possible. David will, I think, summarize or kind of go back into masonry with a few more comments on that, on those ideas. So thank you.
Well, that was pretty impressive. I think Oliver gave us a small cross-section of a big body of work in terms of looking at ways to integrate really a new group of tools, digital tools that we all have, platforms, systems, sensors, and as you all know, design tools that are actually allowing us to really engage more and more complexity. Something that I just wanted to touch on really quickly that I think is really important for us as architects to understand, and possibly for industry to actually see the potential of our engagement in this kind of innovation. Oliver actually presented a lot of things I want to present. What was interesting about this image is that this project was initiated around 2006. And it was not initiated by engineers. It wasn't initiated by industry. It was generally the interest of architects of figuring out, the robot, the kinematics, all of that exists, has been developed before, has been on the market for a long time. What architects were really keen on, and this was initially developed by an architect, was to think, what if we can play with these tools and create new value to them? What if we can bring our initiatives into them? How does that manifest? In this case, it was pretty simple. It was just the idea of, we have this position, and how can we move things in a way that we couldn't have done otherwise? We couldn't have that level of precision and persistence. What kind of systems could that enable us to do? And as architects, I think this is sort of the compelling reason. We like to do things that have an appeal to us, that can speak to us. And with that, it comes clients, it comes interest in where can they actually play a role in our building environment? How do they really manifest? And that was, in this case, in this project from Gramazio Kohler, was the idea that maybe a winery where the grapes are actually, expressed through the facade of very simple bricks becomes a unique opportunity. And then with that idea, that very simple idea of manipulation, a lot of different people start to actually figure out, okay, well, what kind of construction system we do? And as Oliver showed, these things didn't emerge sort of on their own. You start to look at these ideas that architects are generating and try to figure out how does that then changes our industries? How can we implement some of these ideas and become new ways of making, new ways of actually creating our world? So you can see from 2008 to 2016 is a long time, but that sort of implementation becomes much more effective. It also starts to present some interesting economic opportunities in terms of how quickly we can do this, what implications that might have, positive and negative. You can take this as far, and I think in the last one you saw there was about 3,000 bricks a day. There's some people now claiming that you can put 1,000 bricks an hour. And I mean, these are now industry initiatives to actually figure out, well, not only these technologies have a relevance in aesthetic and expressive dimensions of architecture, but also in the way and the speed at which we can actually build. Other interesting that might be also related to masonry is that there are formal potential that were not previously possible. Yeah. So all of these projects are in many ways our interest of architects as designers to then materialize new ideas in unprecedented materials. Another sort of quick project that I'll show, because I think is also of highly relevance to discussion today, is this tool by the Block Research Group, where we're integrating both the design tools. And I'll stop on this one for 1 second, because Oliver presented a huge spectrum of projects. But what's uniquely interesting is that those projects are equally technical as they are intuitive, and they're about design. And to do design with this level of complexity, you need to make complexity accessible. You need to make it in a how to put it? You have to make tools that allow you to, yes, develop an interesting process, but also allows you to tinker with it, to create exclusions, to create unique things that might not fit the pattern. So how do we are able to connect those two, right? Because the arches are wonderful, but how do you create more and more complexity so that you can make them fit in unique context? And that's sort of the work that we are very good at, figuring out how to design and then how to apply those tools. So in this case, the top image looks at the design tool, the bottom image looks at the fabrication tool, which is a five-axis CNC that has a huge blade. And with that combination of the two, you start to look at forms of unprecedented complexity. And this is a masonry load-bearing only structure developed by the Block Research Group. So why does this matter to Waterloo? Waterloo has a history, and obviously we're located in a place where masonry plays a critical role. And as students and faculty, we're interested in all the opportunities that this gives us to express, to investigate, to look at forms of inhabitation. So this is the work of Samantha Oswald, where I think Professor Bordelot was supervising, in which she actually took a very simple idea, which was, you can see here on the image where she has a hand, that's a digitally fabricated mold to actually form a brick, a new, different type of brick with unique properties. I think my opinion is that we could have used some industry help in figuring out how to put the mortar in between, but that's a different story. But what's very fascinating is that, that engagement with the material gave her new ideas as to how these things might actually create new forms, new opportunities, new ways of considering what a conventional piece of masonry can actually do. What can it express? And what we're looking at now, and I think Andrew will explain more on this, is actually looking at new technologies that can also make new connections and explore connections that we might be benefit from. In this case, my expertise being primarily on automation, but also on additive manufacturing, looking at how clay, and ceramics, what they're made of, can actually create new ways of thinking of facades and envelopes that might have new and perhaps unexplored relationships to digital tools and to design potentials. So just a couple of examples of new ways in which many designers, architects, are starting to investigate these opportunities. Clay, sort of make the statement here that clay is of interest to all of us, particularly here, because it's a region known for it, but because it also has a very expressive potential allows us to engage with it directly. It's both low-tech, but it's also high-tech. This is what we use to prototype very complex materials, very complex designs. It allows us to edit. It allows us to really engage directly with it. So it's a very unique opportunity, unlike the projects with wood, that you can maybe cut a little bit, but the precision is untouchable. Here, we can actually go into it and have a much more direct connection. There are also some very interesting advantages. We can actually make products that can be tested, that are accessible, and we can reuse the material. There are other materials that can be engaged with. And I think most importantly, these are skill sets that for students might actually have larger repercussions in the long term. I think additive manufacturing or technologies, whether that's the work that Oliver has presented, work that we have done with robotics, have larger implications on how more and more many of you will actually have active roles in shaping new technologies and new ways of making, new building systems. I'll let Andrea announce sort of more or less sort of what we're planning to do and the incredible support that they'll be providing to the school in actually initiating some of these ideas. What I want to leave you with is, this was an idea by an architect that created a whole sort of level of interest, both from architects and industry to develop. I cannot leave it as what can we as designers bring to the forefront with new and innovative technologies and the support of other industries to move these ideas forward. Great. Andrew?
Well, thank you, Oliver and David. It really is fascinating to see where this is going. And I'd like now to formally announce that MasonryWorx will be moving forward with a partnership with the University of Waterloo. We've started now by, we want to announce that we're providing funds for a 3D clay printer. So the kind of the first step in what David just touched on there. So that'll be in 2018. Yeah, we're incredibly excited to announce this new relationship with the University of Waterloo this evening. This will be a symbiotic relationship that will ensure the masonry industry has an active partner in research and technological innovation to the likes the Ontario market has never really seen before. Allowing the School of Architecture and its students to begin manipulating, rethinking a building material that's been around for thousands of years provides us with great opportunity. This opportunity will also, with talking with Ann and David today, will extend past the clay realm, and I think we're looking into cement and concrete as well. So moving forward, we have the opportunity to utilize the creative capacity of the University of Waterloo School of Architecture and its students to showcase new and innovative uses of masonry that have never been seen before. So thank you. Again, we're looking forward to that. So I can speak on behalf of our membership in saying that we are happy to be working with the University of Waterloo School of Architecture and continue to looking forward to working on this relationship. So thank you, and that's our big announcement.